Hello? Can anyone hear me?
Yes.
Oh, good. I like that shot of Tesla. And someone's recording. Good. There are some great PBS documentaries on Tesla and all the rest of the people who are founders of this movement in the United States in the 19th century. Um, in fact, there was a movie last fall about the current wars, and it didn't do very well in the theaters, but it was about Edison and Tesla and Westinghouse and the wars over whether we would distribute DC or AC as a utility in the United States. It's probably streaming somewhere. I should buy a copy of it. Yeah. Well, he wasn't the CEO. He was the boss of Tesla. He hired Tesla when Tesla emigrated to the United States from Croatia. Anyway, it's 2 minutes into the lab, and I would like to set the agenda for the day and start acting on the agenda by 5 minutes after. Since there's no physical classroom, you could all just like show up on time unless you're coming off of a previous meeting. I, for example, have a collection of class of capstone students who expect me to show up at 1 o'clock this afternoon, and they're admitting that maybe I'll be a little bit late because somebody might have some questions and I may be slow. But I'm glad to be here. Um, so, my agenda for today is to, first of all, survey all of you on a couple of issues. My first question is there anybody attending today who hasn't yet succeeded in accomplishing Lab 0? I'm hearing crickets. I'm hoping that that's good news, that every one of you has figured out how to get Quartus and ModelSim to run on something. Your choices were supposed to include being able to remote into the lab computers, but the IT people got back to me on Monday and apologized and said, no, that's not actually available. It's too hard to get it to work. So that's not available. What is available is a Windows 10 PC or Windows 10 PC emulation on Mac OS. It's also running on one student's Linux machine. And a fourth choice is they claim that there is a remote version of Quartus available. So you can run it in a web browser. I haven't tried it yet. The main reason I haven't tried it yet is because I've been working until well past midnight the last 2 or 3 weeks, composing and testing all these new labs on the fly so that they work, because I'd rather run into the tooling problems myself than have you waste hours and hours running into them. To pick an example, one of my students, whom I will not name, was struggling and didn't get Lab 0 done in time. And he came to me in office hours yesterday, and I hadn't yet figured out how to let him share his screen with me. So I couldn't figure out what his problem was. But in the class lab time yesterday afternoon, I figured out how to let him share his screen. And we all looked at his screens, and I said, let's walk through it, all the pieces. We walked through how Quartus and ModelSim are connected. And in desperation, we clicked open the 3 bullets at the end of setting the preferences and looked at back and discovered that he had 2 different of Quartus installed on his machine, and he was pointing to the version where ModelSim wasn't. So it always failed on him, and he lost a night of sleep struggling with this problem. So we found the right version, pointed it, it worked for him. He's so happy. He can hardly contain himself. And I really, really don't want my students to lose nights of sleep struggling with tools. And we don't get to meet each other, so I don't get to solve these problems in person. I'm grateful that I have figured out how to make one of you a co-host so you can share your screen. I assume that you've all read the articles by now about Zoom bombing, where people get in and start insulting each other on the screens. So the default settings from the University of Washington are that there's only one host, and that's me. And so we're trying to defend you from distractions, but unfortunately, we're defending you from being able to share your work. And I really need to be able to share your work so I can help you. The one new Zoom skill that I'm exposed to but haven't mastered yet is setting up breakout rooms. And we may be able to get through today without needing a breakout room. But for sure, by next week, I need to figure out how breakout rooms work so I can coach you in teams. As some of you may already know, I have 2 strong incentives for being able to have teams. The first incentive is I spent a long time in industry. I went to school at a place that didn't teach teamwork at all. And in industry, business is a team sport. And so our feedback from the industry to the academics is teach them to be team players too, not just technically competent. So I have that incentive. The other is simple. If there are teams, you have the number of lab reports I have to grade, which means I have more time to make up the rest of the class. And so I have an incentive for that. That's that. I do want to encourage you to find teams. If you've already got a team, great. If you haven't got a team, you're not getting to meet each other in person. So if you don't know somebody to approach privately, if you're desperate, send message to your classmates on Canvas, which you're authorized to do, and ask for team players. And if we get through the next 2 weeks and there are still some of you who haven't yet found a teammate, I might do some matchmaking, but I'm going to wait another couple of weeks before I intervene. It's better that you find each other. Are there any questions about that? I'm hearing crickets. I see I only have 10 participants. I think I need to have a few more. So there's some people who are not showing up. Let's see what chat says. Chat says, on average, 2. We have an odd number of people in all of my sections for some reason. So there can be 1 and there can be 3. I don't want to see teams of 4. My incentive for at least 2 is the obvious one of learning to work in teams. My incentive for 3 is simply that given the numbers, that's possibly necessary. But 4, it's important to me that each of you understand the work that's being done, because the exams are individual and the interviews in the industry are individual. And you all need to actually learn something from the classes so that you can have long and happy careers rather than short and unhappy careers. So that's my incentive there. Any other questions before I go on and try to teach you something technical? Because I'd like to do that. That's sort of what gets me out of bed in the morning. Hearing none, I have this thing pointed at my backyard rather than at me, because I think there are some people who would pay money to not have to look at me. My wife is happy to look at me, but she's an exception, not the rule. What I want to do is start sharing a pair of screens, and in one case, I will start changing that screen. The two things I want to share today are the Word version of the lab plan, because we're going to mark it up. And the second thing is a chart from the textbook to show you what the result is going to look like. There's one other thing I'm going to share right now. I'm going to point the camera at, let's see, I think it is sharing. Well, share video. It is sharing video. Okay. I'm going to just show you the solution code. The point of showing you this is not so you can copy it, but for you to understand that the solution code is actually pretty short. And if your color vision is good, you can tell that many of the lines are in green, which means they're comments explaining it. The actual lines of code are maybe 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. There are 18 lines of code there. It's that simple. So let's plan on how to succeed. All right. So moving the mouse here, close that, open that, slide it over out of the way, open that, and now I'm going to share my screen right there. Okay. Now, I assume you can all see it says 425 microprocessor system design summer. Oops, that should say spring. That's dumb. Unfortunately, it's probably going to be summer too, according to what the university president says.
Oh no.
Yeah, she put out a message yesterday that indicates at least the first part of the summer will be remote. And the downside for me is I don't get to see and shake your hands and all that. But the upside is I'm putting a huge amount of time into reinventing all these labs right now. And if it were still remote in the summer, at least I don't have to reinvent them again. I'll get more sleep. I like that. So what I want to do today is walk you through the lab plan, including the testing. And in particular, I want to spend a bit of time on constructing the test vectors. Now, those of you who all went through doing lab 0 noticed that the test vectors were embedded in the test bench because there were only 8 lines of 3 bits each. In this particular case, there's thousands of bits, and that doesn't fit in the test bench. So we will create a test bench text file, and we can create it in any text editor. You can do it in Quartus. We'll walk through that today. So let's make this easier to see. The lab objectives are to simulate and design an ALU. ALU means arithmetic logic unit. Every microprocessor has one at its core. If it's a special purpose microprocessor like a digital signal processor, it may have great multiplying and accumulating powers, but it's still an ALU. In this particular case, we're going to design a simple one. We're leaving out exclusive OR, which is what you did in the last lab. We're leaving out shifts and rotates. We're leaving out multiplies and divides. All we're doing is add, subtract, multiply, and divide. But we're going to start with that. We're going to use the same tools that you used in lab 1. If you have 17.1 or 18.1, they will work just fine. Whatever you have, we're going to draw a target around that dart. So you're going to design this. These are described in great detail in your textbook. In this lab, you will design the ALU in System Verilog and simulate it in ModelSim. So, what's an ALU? Tell me about an ALU. What are its inputs and what are its outputs? Anyone? Come on. There's a hint in front of you.
Its inputs are the numbers that you're inputting, and then the operation that you want to it to do, and then the output would just be the results, I think.
And you're looking at something right in front of you that lists all the inputs and outputs of an ALU.
Ah, the flags then.
Yeah. What is it? What are the results? And to look ahead in real microprocessor code down at the metal, the ALU does most of the code will figure out what things to feed into the ALU. The ALU will do operations, and the results of the operations will set flags, or may optionally set flags. And then instructions that follow the ALU operation will conditionally make decisions based on the results of those flags. We'll learn a lot more about those flags in the next lab, where we are teaching you in the lab and in the lectures about ARM assembly code. So the inputs, two 32-bit long inputs, a 2-bit controller, because we've simplified it down to just 4 operations. You got a result that's 32 bits. You got 4 bits of flags. So that's what's going on. You are in this lab going to create a simplified ARM ALU and see what it does. There's a comment here. An adder is a long chain of cascaded exclusive OR gates. And exclusive OR gates are relatively complicated compared to simple gates like ANDs and ORs, NANDs and NORs. So it needs more transistors, so it's relatively expensive. So it's optimal to have one adder piece of hardware. And so a common approach is to make a device that does add or subtract in 2's complement. And one of the control bits is used to take the second operand and use it directly, or make the 2's complement of it and then add it together to the other operand. We're going to get there. Okay? And again, this is all described in your book. The 4 operations are, no, we'll get there right next. Right. These are the results. Well, I'm going to go back and forth and tell you what these are after I tell you what the controls are. We're going to do addition and subtraction. And those impact the sign bit, the 0 bit, the carry bit, and the overflow bit. In Verilog, the syntax for addition is plus. There are some logical languages where the plus indicates or and, but in this case, it's the one you learned in first grade, plus symbol, and subtraction is the minus symbol. And the syntax for the inversion of something is the tilde in front of it. Okay? And so I'm going to go back and explain how those are impacted, but this is a numeric operation. So any operation affects the sign bit and the 0 bit. And arithmetic operations have a carry in and a carry out. The carry out is here and overflow is here. All right? And ORs don't generate carries and they don't overflow, but they do generate a sign bit and a 0 bit. This here should be a comma. And this here should be a comma. Oh my. All right. So back here, you all understand 2's complement math by now, correct? Is there anybody who, because we teach this in 271, and if you transfer it in from another school, they should teach you 2's complement by now. So I assume you all understand it. Okay, so the sign bit is the most significant bit. So in 2's complement math, the numbers that you can represent, let's suppose it's a 32-bit number. Or let's go back. Let's suppose we're talking about 8-bit numbers for a moment because it's easier to say. If you have an 8-bit number, the maximum number you can represent is plus 127. And the smallest number you can represent is minus 128. So that's 256 different numbers that fit into 2 to the 8th. So any operation that's negative will set the high bit. So that's bit 3 of the status register. Is any bit positive? If any bit's positive, any bit is on, it is not 0. We'll talk about how to generate those. If it's an arithmetic operation, it can generate a carry out, and that fits into bit 1. And if there's an overflow of the result, that means if I add 2 numbers that add up to larger than 127, it'll overflow. If I subtract 2 numbers that results in a number that's even smaller than minus 128, that's an overflow. So we will have logic in our system that detects an overflow. We'll talk more about that later. If anybody wants to stop me, just unmute yourself and speak. Because if one of you has a question, it's likely that more of you have the same question in your minds. And the brave one will get my attention and you'll all get the answer. Right? So those are the status flags here, the control inputs, simulation and testing. You need to figure out, in this class, we don't get to toggle switches and have them flow into our DE1 to make combinatorial decisions. We have to come up with what the test vectors are. Like I said, in lab 0, there were so few test vectors, only 24 of them, that they just fit directly into the test vector. In this particular lab, and in all your future labs that use these tools, you'll create test vectors. So matter of fact, for the class project, which will be to simulate an ARM CPU, you will develop the test vectors in lab 3. We'll get there. What I'm going to show you in this lab plan is a table that's not all filled out. And a large fraction of the time today is I'm going to explain to you how to finish filling out this. Now, there's a lot of bits here. In fact, there's 2,040 of them, which again won't fit into the test bench unless you want to make a really long test. Okay. So if I were to fill out this table, I need to understand how arithmetic works in 2's complement and how logic works in 2's comp. So in logic work, it's bit by bit. So I've proposed here a series of examples and some exercises. They'll all show up in the table. If I have 4 bits, and so this is 4 ones, and I do a logical AND with 4 zeros ended with 4 ones, the result is 4 zeros. if I take the dual, if I OR 4 zeros with 4 ones, I get 4 ones. Is that mysterious to anybody? That's an easy one because they're all the same. Let's suppose I take alternating all ones and I AND them with a different non-overlapping all ones. So this is 0, 1, 0, 1. This is 1, 0, 1, 0. If I AND them together, the result is still 0. If I OR them together, the result is still all ones.
So does
Okay.
this perform like the OR gate on each individual pair of bits?
Exactly. That's
Okay.
the point. It's a bit slice through the entire ALU. There are 31 of these things operating in parallel, 32 of them operating in parallel. I keep having to switch back and forth between counting like a programmer and counting like a regular person. So if I take the same, here's some that kind of overlap. If I take 4, which is 0, 1, 0, 0, and AND it with a 5, which is 0, 1, 0, 1, the AND of it is 4, but the OR of it is 5. Because they line up in the bit 2 position and they don't line up in the 0-bit position. Okay? Now, what do you think happens if I AND 1 and 8?
The result will be zeros.
Yep. And what if I OR them together?
9.
Correct. And what if I AND 3 and 6 together? Anybody? It's okay if you draw it out on a piece of paper and
Is
look
it a
at it.
4?
No, actually it's not.
Okay.
If you have 0, 1, 1, 0, that's a 6. And 0, 0, 1, 1, that's a 3.
Oh, so it's 2.
And correct, it's a 2. But if you OR them together, what do you get?
0, 1, 1, 1, which is 7.
Correct. Well done. All right. I think you're going to do well in this class. All right. So to run this simulation, you need to do 2 things. You need to create the code, and you need to create the test vectors for the code. Now, to create the test vectors of the code, I give you some partial examples, and I include test vectors for the first like. So let's suppose you get to look at these things and figure out the rest of this thing. So obviously, if I add, numeric add a 0 and a 0, what is the result going to look like? I'm going to start calling on you people.
It's going to be zeros.
Right. And if it's a 0, there should be the bit, if you're counting hexadecimal, bit 2 of the forward bits will be set high. So that'll be a hexadecimal 4. Right? So let's start saving this. I'm going to save this because we're going to fill it in, parts of it in, while we're here. And this one is going to be lab week 2, and the AB, the other section.
Will you be posting this or should we fill it
No,
out along?
no, you should be taking notes. You can do a screenshot, because what commonly happens when I do this lab, I project it on the whiteboard, except with the screen up. So when I start marking on the whiteboard in front of the students, some of the students take photographs of the screen,
Mm-hmm.
but I still need you to actually understand why all these things are true.
Yeah.
So what I'm going to do right now is, right? I'm going to save this, and you can pay attention if you wish, but I'm not going to post them.
Okay.
So this one here, guess. Sure. I'm going to slide up. So it's a flag. 0, 1, 2, 3. These are the bits. So if this bit is set and these are clear, it's a 4. This bit is set. These bits are clear. It's an 8. Okay? Does that make sense? It's not negative. Yet in this particular case, the most significant bit is not set, so it's not negative. Whereas in this one, if I take -1, if I add -1, that's the 2's complement of 1, and add it to 0, what's my result going to be?
All F.
Exactly. And the most significant bit is a 1, and that yields an 8. Okay? So what I'm going to propose that we do is we're going to walk through these and figure them out. And then maybe walk through some of these and figure them out. So what happens if I take +1 and -1? Well, we know what -1 looks like. It's right there. And what result do we expect?
Zeros.
Yeah. And what result do we expect to see here?
0.
Well, no. Which bits will be set and which ones won't be set?
It'll be 0, 1, 0, 0, so 4.
Correct.
Oh, those are
But-
the ALU bits?
It could be correct, but if I add these together, all 1s and a 1, what's going to happen out carry?
It'll be 1.
Correct. So it's actually a 0, 1, a 1 for the carry bit, and a 0. So this will actually be 6. And to illustrate that, when we handed you those first bits, that's what they look like. To make this look a bit easier, we're going to make it courier new so they're all the same length. Okay,
I apologize. Could I see the flags again?
sure. You should have a copy of this open on your own screen.
I will do that.
Yeah. So you can flip back and forth between looking at the shared screen and looking at your own. Yes? I'm not real good at drawing this stuff yet, but I want you to look at these things right here, right now. Okay, so if I do an add instruction, so I have an ALU and I feed into it a 1 and all Fs, and I'm feeding in a 0 because it's an addition. Well, a 1 added to all 1s is going to be equal to 0, and the additive result is a carry out. So when you do that, the carry out bit will be set. That's bit 2. I'm sorry, bit if these are numbered 0, 1, 2, 3 in the flag data structure, then that's setting this bit and this bit. And this is clear because it's not negative, and this is clear because there's no overflow. So that's going to be 0, 1, 1, 0, and that's a 6 in hexadecimal. Does that make sense? Right. And thank you for that question, because those of you who are silent probably needed the same explanation.
Yep.
Correct. In this case, there was. All right.
Could you explain the carry out? I don't fully understand that in this
Well,
scenario.
I'm adding all ones to a 1. So if you were to work it out by hand, 1 plus F is 0 with a carry. That carry in plus F is a 0 with a carry. That carry out, that ripples through the entire chain. So the result will be 0 with a carry out from the most significant bit.
Oh, so you take that 1 and then you add it to each of those Fs?
Yes, and each one of those Fs generates a carry out.
Okay.
If you were to construct a 4-bit ALU and process this entire thing in a loop, you'd still wind up with a carry out.
Mm-hmm.
Capiche?
Yeah, I think I get it.
Okay, well, we're going to walk through a few of these some more. And here, we're going to do a simpler one. We're going to add 2 Fs, not 8 Fs, to 1. So what's this operand look like? Correct, right? So what do you think the result will look like?
The third digit would be 1 with a carry out.
No. Yes and no. What's true is there is no carry out, because if I add 1 to 2 Fs, the result is 1 and 2 zeros there, but there's no carry out of the entire 32-bit operation. So in this particular case, what do you think? There's no overflow. The number fits within the range of numbers that can be represented. There's no carry out. It's not 0, and it's not negative. So what do you think the status bits will be? Correct. I'm walking through this because I want you to all understand this. All right, so we've gotten through the first 4 lines. There are 16 of them to go. We're not going to go. I don't
quick
think.
question.
Yeah.
Where are you getting the definition for the status?
I will explain the status definition in detail later, but since you're asking the question, let's define it now. Again, it's this 2's complement arithmetic. So the most significant digit is the highest bit, period. Are any of the bits set to 0 or not? Or excuse me, are any of the bits positive? So if any of them are, this bit is 0. If all of the bits are 0, then the result is 1. Have any of you ever understood the reduction operator in Verilog before? Because you might have learned it in, where are we here? This is the test bench, right? I'm actually teaching a more detailed version of this in the 271 course in the next lab. In the reduction operator, let's see. How many of you have actually looked at the IEEE 1800 document that I posted? It's pretty large. I don't expect you to have memorized it, but I expect all of you, if you need to figure out stuff, you can use your 271 textbook. You can look for these operators in your Harrison-Harris textbook, or you can look in 1800. The reduction operator, I'm going to just sort of show you what that might look like. Because this is the test bench. Nope, I didn't include it. So I'm going to type it in and erase it. If I wanted to generate the zero flag, I can assign the zero flag equals not the reduction of result. Here's what that means in Verilog. Putting the operator in front of this thing, this is a 32-bit thing, let's say. The reduction operator means that it looks at all of these bits. If any of them are 1, the result is 1. And then this operator just inverts that. And that sets the Z flag to that. That's the operation. Just screen capture that because I'm going to erase that. Everybody ready? Write it down on a piece of paper. All right. That's how to generate a Z flag.
Joe, can you put that back, please?
This is called the reduction operator. If you go through the standard 1800 and search for reduction, you'll find this definition. If you go to your 271 textbook in section A.7, there's a little table. It shows the reduction operator. Capiche? Are you ready for me to erase it again?
Yeah, thank you.
Okay, so somebody wanted to know how to generate some of those things. So I just told you how to generate the Z flag. This is just clipping off that bit. This bit is produced by the carry or by the adder. So how many of you remember concatenation? Let's suppose what we're going to do is another bit that I'm going to erase. And let's suppose you define a C bit for the carry. And we'll write assign C. What we're going to do is concatenate. Use the curly bracket C, comma, result equals A. We're going to do two things at once here, so I want you to pay close attention. A, Verilog syntax for plus. And let's define a subtract number, which is equal to the least significant bit of the controls. So let's suppose we have assign the subtract bit equals ALU control bit 0. And I'm doing that for convenience. You can make longer things and drop that all out. But let's suppose subtract bit is that. You could make it more elaborate and you could say subtract bit equals ALU control and make this small. So subtract is set if it's this row here. This is 0 and this is 1. Okay, let's do that. So let's define subtract as a single bit. And then we're going to use it here. How many of you have seen the conditional logic definition? Again, if you search for conditional logic in the Verilog standard, or you search for conditional definitions in your 271 textbook in section A, period 5, you'll find the same result. And so what you'll do is define a piece where I say subtract bit question mark. So this little piece of conditional logic is a 2-input multiplexer. And it says, what do you want to do if it's set to a 1 or set to a 0? I'm going to use not B if it's set to a 0 or set to a 1, or B if it's a 0. So I am just adding up the first operand and then conditionally either the second operand inverted or not, plus subtract bit itself. This piece of logic here will do two things at once. It'll perform either the add or the subtract function and put that into the result, and it will generate a carry. I want you to write this down on your piece of paper or do a screenshot. Any questions about how these work before I erase them? Yeah. Yes, you can. I want you to, this is simpler because I'm using an operation that you should learn about. And one of them is concatenation, which is a standard Verilog and system Verilog thing. And you use these curly brackets. And you can use the conditional statement in Verilog, which is essentially an embedded 2-input multiplexer. Now, you can do all this in more lines of code, and the result will be the same, and it will test the same. But I'm trying to teach you these bits because they'll save you a lot of trouble in other places. Now, I sent out Canvas email 2 days ago, I think, that included the Zoom coordinates for my office hours on Tuesday and on Wednesday. I also sent out email on Canvas that says, I'm not taking tech support questions on Sundays, period, full stop. There's one day that my wife owns, and that's it. And the other is, if any of you have questions and you ask for my attention, and I agree to meet you at a certain time, I will be quite annoyed if you don't actually show up. One student asked for my attention, and I agreed to meet him, it was a him, on an evening late last week, and he didn't show up. I waited for a half an hour waiting for him to show up, and I didn't do much of anything else for that half an hour. It turns out that he had decided that he was successful, and he wrote me a piece of email, and he trusted autocorrect to complete it, and he sent his "I'm done, I don't need help" message to someone other than me. So I didn't know that he had succeeded. So he didn't tell me that he hadn't succeeded, and I wasted a half an hour of precious time waiting for him to show up. Please don't do that to me. Thank you in advance. Now, so yes, I will try to help you, but I'm not 24/7 available. And I'm particularly not 24/7 available if you ask for it and I set a time and you don't show up. So this is a chance for all of you to learn to be competent communicators as well as competent designers of logic. Capiche? Right. So I'm going to erase this because you've all seen it. Let's go through and figure out some of the other math stuff, in particular, demonstrate what overflow looks like. And then we'll declare a bio break, because I don't expect anybody pays attention constantly for 2 hours. All right, so let's suppose we're going to add two numbers. It tells you what the second number is. So what's this going to look like? Come on. Hello? Anyone?
It's
The
gonna look
9
just as it's
zeros?
written, with a 5 and 7 zeros.
Oh no, yeah.
Right. And
5
so
with
what's the
zeros.
result going to look like?
A 9 and zeros?
Yep. So what's that going to produce in terms of status bits?
Nothing.
0?
Nope. Wrong on both counts. First of all, it's going to be negative. The 0 flag will be clear. The carry out flag will be clear because it doesn't generate a carry out. And what do you think the fourth flag will be? Has that number overflowed or not?
Because we had to go negative because we're using 2's complement for that last digit.
Yes. And so has it overflowed or not?
Yes.
That is correct. I designed this on purpose just for fun, so that 9 is the same as this 9, but they're the same for different reasons. Okay. Now, overflow happens if you add two numbers that overflow from the range, or if you subtract two numbers that overflow from the range, because this number here actually looks like -7 large if you were to interpret it, but you want to catch the fact that it overflowed. Here's why overflow matters. How many of you have ever been attacked by malware before? How many of you ever got a virus on your computer before?
I have.
Yeah, and
Something
it's an
true.
unfortunate problem. I opened a piece of malware by mistake because they impersonated someone else at the University of Washington. So I had to, fortunately, I was regularly backing up all my files. So I completely reformatted my hard drive and reinstalled all my applications and reinstalled all my data. The vulnerability that allowed that malware to be installed is that some software in either Windows itself or an application running on Windows doesn't check for out of range values. And when it gets hit with out of range values, it breaks in various ways. And when it does, it opens up vulnerabilities that allows rootkits to be installed. And that malware now can monitor all my keystrokes or do all kinds of other skullduggery to me. If any of you ever get hit with ransomware, that's the way in. And then you have to pay somebody money, probably in Bitcoin, in order to recover your files. This has been happening especially to a lot of public institutions like universities and hospitals and governments, is that there are people out there actively looking for people with money and with valuable data to force them to pay them. And the overflow bit, if it's not checked by software, is the key vulnerability. So you should take these things. If any of you ever go off and create data, you have to create data processing work that can handle unexpected data as a result. Okay? And that's why the overflow bit matters. So let's figure out this other one and then take a bio break. So let's suppose I want to subtract two numbers, the result of which will be out of range. So if you do the 2's complement of 3, it looks like D and all zeros. If you were to create the 2's complement of 7 and all zeros, what would that look like? And I'll give you a hint, you've already seen it. If you were to write out on a piece of paper, what does -7 in 4-bit numbers look like? What would it look like?
9 and then all of the
Correct.
rest.
Okay. Now, if I were to take an adder and stick D and 9 together, what's it going to do?
It's going to equal 5, and then the rest zeros. It's going to be negative. There's going to be overflow and carryout.
I think you're correct.
So it's going to be A for status.
Because it will be negative, but it won't be 0, and it will have overflowed. No, it won't be it won't be if it's. Let me check that out again, because I threw away my notes from yesterday. If I add 1101 and 1001, it's going to be. It's actually going to be a 6. It's not going to be a 5. It's going to be a 6. It's going to be an even number. And it's going to be an even number because both of these are odd numbers. So it looks like +6 when what you really want is -10 or -A. And so it's not negative. So the most significant bit is 0. It's not all zeros, so the next bit is 0. It did generate a carry out from that operation. So the third bit is a 1, and the least significant bit is an overflow. So it'll be 3. Does that make sense? I'm going to save that, and I'm going to declare a bio break for 10 minutes. So I'm not going to try to teach you anything new for the next 10 minutes, although I'm not taking that away either. What we need to do in the rest of this hour is to talk about how subtraction works, what the logical operations will produce, how to produce a test bench, which is basically handed to you, except that you're probably going to change any of the names that you wish, and how to create that test bench. Okay, that's the plan for the next 10 minutes. I actually saw a beaver outside my dock this morning. It was great. All right, I'm back from my break, but I'm still going to wait till 10 after, another minute. Has anyone on the call opened up their textbooks and looked at the text on how you build an ALU?
A little bit, yes.
Good, good. I'm actually leveraging this a little bit. I'm also the lab instructor for 271, and they don't get to meet in person either this quarter for obvious reasons. So I've taken this design and I've simplified it to 8 bits instead of 32 bits, but it's basically the same lab. And it's the 271 Lab 2. So they're 2 weeks behind you on a simplified version. And the other difference is for them, I threw in the exclusive OR as well. And see if they can do that. I'll bet you they can. All right, here we are. Let's pick up where we left off. We had, in our previous episode, walked through constructing these test vectors, all the additions. So let's try some subtractions and some logical stuff and then figure out how to test it. Okay, so imagine we're going to subtract 0 from 0. It's kind of obvious that it's going to be all zeros. And the result is going to be kind of obviously 0, but what do you think is going to come out of that thing? In particular, it doesn't overflow and it's not negative. So it's a 0 in those places. It's a 1 in the 0 flag. The question is, does it generate a carry out? If you guess is the same as mine, you might think that it doesn't, in which case I invite you all, when you're testing it, to actually see what your logic does. Sometimes it's worth experimenting to find out. So if we subtract -1, what do you think we're going to get out of that? What do you think the result's going to look like?
1.
We're expecting a 1 to come out of it. So it's not negative, and its sign is 0, and it doesn't overflow. Am I going to get a carry out of that?
Yes.
Based on the logic, let's suppose the logic that we just talked about defining. So we're going to complement the second operand B, so it's all zeros, and then we're just going to add a 1 into it. I think that the result will be no carry. And I think that the status will be all zeros. I predict that that'll happen. And I invite you to test it and find out. In contrast, let's suppose we take 1 and 1 and subtract them. Well, obviously the result's going to be 0, But how are we going to get there? If we make the 2's complement of 1, and then add a carry into it, I think we're actually going to generate a carry out. What do you think? So obviously the 0 flag is going to be set. So that's bit 2, and it's not negative, and it's not an overflow. So do you think, based on the logic that we've been talking about, whether there will be a carry generated or not?
I don't think so.
All right, let's guess that that's true. I invite you to test it, of course. So here we're going to take this number and we're going to subtract, and what do you think we're going to get from that? That should be fairly straightforward in terms of results, and let's talk about the status flags. What do you think the binary is going to look like, or in hex? Hello?
Gonna end with 2 Fs.
Yep. Right. And
Question.
yeah.
For the previous one, is it going to be a carry because it's actually going to add all Fs?
Well, the
The
carry out in subtraction is the inverse of borrow. In fact, I think I made that
Okay.
I made that explicit here.
Okay, so never mind. No carry then.
Right. All right. So, and it's not 0. So it's all the bits are off. No carry, no borrow, no overflow. It's not 0, right? So saving that. Now let's have a little bit of subtraction fun, shall we? So we got this, and we know what -7 looks like. It's 9. Now we're going to be subtracting. So we're going to invert those bits, but it's going to look a little different because it's not going to, yeah. What do you think the result's going to look like here?
B followed by 7 zeros.
Yeah, and what do you think the status is going to look like there? It's going to be negative. It's going to be not 0, so 1 0. There will be a carry out, I think, and it's overflowed. So what's the status going to look like in hexadecimal?
B again.
You got it. I did that deliberately. Just for a small bit of math humor. So let's try -6. And this is a typo. Should be 7 zeros. So -6, what's that going to look like in 2's complement?
It looks like A.
Well, 8.
A like alpha.
Yeah. Right? So that's what the initial 2's complement minus 6 is. Right? Good. And we're going to create plus 5. We're going to subtract plus 5. So that's all these guys. Right? So what's that going to look like? We're thinking that it's going to overflow because we're subtracting it. So what do you think that's going to look like? And a hint is it's going to be an odd number, not an even number in the most significant bit. Sorry, most significant digit. It's going to wrap around. So the 2's complement operation is going to flip all those bits so that 5 and all 1s will turn into an A and, I'm sorry, a 5 and all 0s will turn into an A and all 1s. And then you'll add a 1 to it. So it'll look like 6. Yeah.
Isn't it going to be all zeros with the carry?
Nope. Because we're subtracting, not adding. So the complement, I'm going to put in here the complement of this. The 1's complement. And the 1's complement of this is A. Okay, that's what's going to go into the adder with an additional 1.
So would the result be 4 FFFFFF?
No. The result will be something in all zeros. But the question is, what will the result look like? Because it's going to wrap around. And
Isn't it just 5 again?
as a matter of fact, it is. Coincidentally, it's 5, but that's because we're wrapping around. And so it'll generate a carry. It'll generate an overflow. It's not 0. And it's not negative. So the status will be 3. Make sense? Just for perspective, when you flip this guy around.
Are you saying that the adder, in addition to the 2 numbers, is also going to have a carry in going?
Well, yes, the carry in is generated. Remember when I drew you that logic that said assign the carry concatenated with the result equals A plus the conditional on the 2 or the 2's complement, and part of that was to add in the subtract bit itself. That's the carry in.
I see. So it's essentially like adding B with all zeros rather than A F F F F F.
Correct. So what I've just drawn here is what happens if I did the 1's complement of 9 and all zeros. And that's actually, that's a 6 and all ones. So if you throw this and a 1 into an adder, you get that. And if you throw an A and all ones and a 1 as a carry in and this into an adder, you get that as the result. Does that follow?
Yes, I get it now.
Good, good. So let's shake those arms out and let's try some logic. What's that going to be? And this should be easy.
All Fs.
Yep. And the status should be simple. It's negative. There's no carry, there's no overflow because it's not arithmetic. So it's that. If I do the same thing here, if I end all ones with this, what do I get?
1 through 8.
That.
It's all ones again. Okay.
Wait,
And-
wouldn't it be 1, 2, 3, 4, 5, 6, 7, 8? Because that number has got
Correct.
converted to binary is going to have the zeros, and those bits are going to generate zeros for the AND gate.
That's right. I was too quick. You AND them all, and that's what you get. And it's not negative, and it's not 0, and it didn't overflow. So that's what it is. Now this one is easy. If you AND all ones and all zeros, it's all ones again. And that's true. But what do these look like? This is more interesting. What happens, as I was specifying above, what happened if I AND 1 and 8?
You get
There's
0.
no overlap, so it would be 0.
Correct. And in the
But
next case, if I look for
why
the
is it on
overlap
the
of 2 and 7, what do I get?
2.
Yep. And if I look for the overlap of 3 and 6, what do I get?
1.
Nope. Line up 0 and 3 ones.
2?
Yes, correct. So there's 2 unspoken for and there, right? No, that's not what I wanted to do. So we've got to figure out what these are. So what's 5 overlapping 4?
4?
Yep, twice. Oh, what did I just do? I wanted it here. All right. So that's overlap is there. And it's not negative and it's not 0.
Wouldn't the next one be zeros, not Fs?
Correct. I did that on purpose.
Yep.
So, but this one is all zeros. So you set the floor flag. So here's overlap in the opposite direction. Obviously, if you OR them all together, that's going to be negative. And now we're positive overlapping, so everything is wall ones. Now we're positive overlapping rather than negatively overlapping. So what do we got here? 1 and 8 or 8 is what?
9.
Correct. 2 and 7.
It's still 7.
Correct. And 3 and 6 is
Also 7.
correct. And 5 and 4 is
5.
yep. And
Interesting.
it is negative and not 0. So you see what happened if you positively and overlap them and or overlap them. You get different results. And here we're overlapping, and this one is going to be, I think you all understand. Eight. So that is our set of test vectors, logically.
Nice.
So what you're going to wind up doing is creating something with 20 entries that all look like this. Here's the control entries, A, B, output, and status. And this is apparently what ModelSim expects, so this is their format, not ours. So you use underscores to break these things up. So you create one of those. You type it in. You can use, Quartus to do this, or you can use any text editor, but you want to save as, you want the extension to be TV as in test vector. Now you could name your module something else than ALU, but ALU is pretty short. And if it warns you that you're saving a text document, you go like, sure, that's what I want. And now you need to create a test bench. And you can actually get away with putting this into the same file, or you can put it in a different file, but you can make your own sample ALU test bench file. Now, again, I gave you an input, and this could have been, of course, blue, in which case this is red, and that's red. This is what Quartus will do when you type these things in, if you're in Quartus and not in a plain text editor. And these here are all going to be blue. This is what Quartus will do to them, because these are all keywords. Now, you can make these simple A and B. You can shorten these results, do whatever you want with them. The advantage of doing that is it's easier for me to tell that you aren't cheating. You can name them colors, you can name them after football teams, you can name after them any random thing that's easy to write. So what is important is that the names of the variables here match the names of the variables here. So if you change them somewhere else, you got to change them here. They all got to be the same. Now, this is unnecessary. This can be like 103 or 102. Actually, since I'm counting like a programmer, it can be that. And you need to reference the DUT means device under test. Make sure all these names match or it won't find them. This little piece of the module defines a parameter, which is a clock period. And basically it means the simulations are logically in picoseconds, which is insanely small. But so it means on a clock period of 1/10 of a nanosecond, every 50 picoseconds, toggle your little simulated test clock. So this piece, you remember in Lab 0, you had your test vectors embedded in the document. Here, you read them in, so you have a read memory operation. And ModelSim will think, oh, or Quartus will think, I need to go find this file called ALUTV and read it into the test vectors. So 20 times, it will read strings that look like this into the test vectors. And will feed the first bits into your simulated ALU and create the results. So then you'll feed them all into the output. And I'm going to show you approximately what the output will look like. And I need to share that. So new share will be that.
I see it already.
Ah, okay. So there'll be 20 columns, and you're looking at all these results. And a hint is that if you leave it to the default, it might give you binary, which means all these columns will be really big. And so it's convenient for you to walk along here and set the radix to hexadecimal instead of binary or decimal, because that makes them smaller and easier to see. You see, here is the results, and here's a 4 and an 8 and a 6 and a 0 and a 9 and a 3. These are the first 5 operations. Here's what those inputs and the control input. Here's A and B and the control, right? So I'm sharing these photographs just so you have an idea what success looks like, right? So let me go back to sharing the main screen. The other thing I could share, this thing shows a whiteboard, except I don't know where the whiteboard is. The other thing I was thinking of sharing was, I want to share this. This is an illustration. All right. So I need to move things around. Can you all see this illustration, which is from the textbook?
Yes.
Yep.
Okay. This is a symbolic representation of what you'll build in System Verilog over Quartus. So there's a 4-input multiplexer, which you can build with a case statement. One of the cases will point to this stack acting as an adder. One of the cases will point to the same thing acting as a subtractor. If you use a case X statement, instead of a case statement, you get to say case 2B apostrophe B0X. So it selects the same stack either way. And then case 2B10 collects the assignment of an and. So A ampersand B, and case 2 apostrophe B11, you assign the results to be A or symbol B. So that result creates the result. Name it whatever you wish. And then the N flag is basically the most significant bit. The Z flag is that reduction operator on the entire result. The C flag is generated by the same logic that generates the sum. You just capture it as the C flag. And then this logic here generates the overflow. So the overflow is the AND of 3 terms. One of them is a bit that says this is a logic operation. So you take the most significant bit and invert it. So if that's true, and either this case, the most significant bit of the sum exclusive OR, the most significant bit of the first operator, or this 3-way exclusive OR, that combination of things tells you that it's an overflow. So we have about 20 minutes left. You could go off and I'll try to build it now and tell me if you run into any problems and share those problems.
Question.
Yeah.
Would it be all right to use actual gates instead of case statements to build the multiplexer?
You can build the multiplexer any way that works.
Awesome. Thank you.
You can build a single bit adder as a module and then build a complete module that uses all 32 of them. That's going to be much more code than you need, but you can do that. You could build a modular ALU function and then build a 32-bit ALU function by calling those 32 times. You don't need to do that. That's working too hard, but you can do that. Like I say, this code that I was showing you is 18 lines, and the rest is commentary. To me, the most interesting / difficult part of this is making sure that you can create the test vector and that you name everything correctly so that the test bench finds your test vector and uses it correctly. 2 weeks ago, I had to call up in desperation a former student and TA named Shauna Cabanday because I was trying to repeat all of this stuff and she found all my typos using Zoom. And so I have repeated this work 2 weeks ago, so I know this works. Although it'll be interesting, I have to simplify and repeat this work for the 271 lab, and I haven't done that yet. The big thing I did in the last 24 hours is I decided what the last lab in 271 is going to be and got it all nailed. So I'm waiting for questions.
Would it be okay to test this on a DE1 SoC board instead of using the simulation?
You would, the difference is you could, if you've got a DE1.
Yes.
In a DE1, you have to figure out how to input the values. And a DE1 has no provisions at all for you to enter 32 bits of input. So you would have to redesign your code that ran on the DE1 so that you could enter, let's say, 8 digits at a time.
I see.
And you can't display 32 bits of input. You can display 24 bits of input at
I could
most.
assign one of the switches to display the remaining digits. Just show part of the digits on one screen, and then
It'll be
the rest
interesting.
to show the rest.
Normally, this is actually a normal lab for 425 for the tech classes that I and Kaibo teach. Because, you know, that we use a system Verilog over Quartus because you can't put operands this large into the DE1 directly. You follow what I'm saying?
Yes.
Yeah. Whereas normally in 271, you use the DE1s and you load stuff into them. So for my second 271 DE, I'm sorry, my second 271 lab this quarter, which is normally building a 5-bit adder because you have 10 bits of input on a DE1. So you can put in 2 5-digit numbers. In this new version of the lab, you will build a separate test vector, just like you're doing now, but it'll be for a pair of 8-bit numbers rather than a pair of 32-bit numbers. So they'll go through a similar exercise 2 weeks later of figuring out what all the different operands and results would be. And they'll have similar logic, but it'll be simplified. They'll also add a 5th function. They'll add exclusive OR. Because I'm simplifying parts of the lab and I'm trying to add more complications in a different way. Since they've all gone through exclusive ORs in Lab 0, they'll understand how to do exclusive ORs. And in their Lab 1, they're going to do a hex to 7-segment decoder. And they're going to learn Carnot mapping in Lab 1, which they need to learn. I think that the professor is going to start talking about Carnot maps on Monday. Somebody's got a cat as their picture. That's cool.
Sorry.
No worries. That's not a problem. I've been, showing off my dock instead of looking at me. So, hey, it's all right. It turns out that there's a feature in in Zoom, where you can choose a fixed background and the software attempts to actually fit you into that background. It works if it's a solid color, and it doesn't work very well if you make a photograph like that your background. The software has trouble with that.
Zoom has a similar feature, but you have to have like a green background behind you, specifically a green background.
Right. Right. And I don't have a green screen behind me. So yeah, no, that's actually a Zoom feature, and some of the professors are using that now. whereas Dr. Kim just has the background in his room behind him. And I have, if I switch, if I change this to True Vision, you're going to be looking at me straight out of my computer. Right? Like I say, some people would pay money to not see that photograph. It's all right.
Excuse me, Joe.
That's not true.
Yeah,
Could you re-explain the status part again? When you,
sure.
Yeah, I'm not 100% getting that when I'm running through this again.
Okay, so what you're currently looking at is the block diagram, correct? That's the screen I'm sharing right now.
Yes, that's correct.
Good. So status. One status, the simplest one, in 2's complement, the most significant bit of the result is the N flag. That's easy, right?
Yeah.
And the next easiest bit, I have to snooze for my capstone. Oh, I didn't want to dismiss that. I have a capstone meeting. It's at 1 o'clock sharp. If you want to generate the 0 flag, do you remember earlier in this discussion, I showed you and then erased an operation where I said assign Z equals inverse of open paren reduction, which is the OR operator applied to the result, close paren. That
Yeah, I
logic
remember.
actually works. Okay, so that gives you the first 2. The carry bit is where you assign the concatenation, which is the curly bracket. So imagine you've defined a C variable, single bit. So you assign open concatenation C, comma, result, close curly bracket equals. Then that long expression of A, the conditional bracket for the 2's complement, and the subtract bit itself, semicolon. So one long operation, the thing that generates the sum, it generates a 32-bit result and it generates a carry out. So you grab that carry and that becomes your carry flag. That's the first 3 of the 4, correct? Follow that?
Correct.
Okay, now the question is, how do you generate the V flag? Now, in this solution, this solution was done earlier, but this is another solution. This piece of logic, if you can see it, nope, I don't want to do that. This logic here, where it's equal to the inverse of the end of a control bit, exclusive or this, exclusive or that, and that exclusive or, and the inverse of that logic. This logic here is Verilog syntax for this logic here. The inverse of a control bit and this exclusive or and this exclusive or. That logic collectively generates the overflow logic. This is also explored in detail in the textbook, and it's explored in detail in your 271 textbook.
Okay, thank you.
All right. And again, I invite you to build this and then look at the actual results. And if the actual results don't match what you predict, see if you can figure out why.
I have a question about the diagram.
This one here,
Yeah, what is that /n?
/n.
Yeah, it's kind of all over the diagram. Yeah,
Oh,
that right
okay.
there.
That means it really means /32. It's saying this is a
Oh.
32-bit wide data path. That's a 32-bit wide, 32-bit, 32-bit, 32-bit.
Okay.
Whereas this means there's 2 control bits coming in. There's no slash on here, which means it's 1 bit coming in. This one also means 32 bits wide. Whereas this one is specifically referring to the most significant bit, counting as a programmer from 31 to 0. So this is the 2 most significant bits of these 2 operands. Again, these /n's mean /32. It's a good question, and I'm glad that all of you were here to hear the answer. Whereas this specifically means that there's only 4 bits. That help? Good question. I'm waiting for another question to come flooding into your minds. I hope I exhaust them all now because I've got a capstone group that starts up in 4 minutes. And I'm going to have to be late. The question is, how late will I be? So meantime, I'm going to go back to share the other screen and walk through the tail end of it. Okay, simulation and testing. We'll build the test vectors. We'll save the test vectors. The test bench will reference the test bench itself will reference the module itself. And then what do I expect? What I haven't done so far is said, here's my model report. Because you guys are all adults, believe it or not. And I expect you guys to, and ladies, to decide what an adequate result means. What I'm fundamentally interested is evidence that you've actually done the work, so you've actually learned something. That's what my top marks go for. Style matters less. And I also know that many of you, English is not your first language. So you may have style issues that have to do with English not being your first language. I forgive those things. I'm interested in whether you learned this stuff. So I do want to know who your team members are, because the first thing I do when I harvest all your results is I go down and account for everybody. And the reason I wanted those 3x5 ID cards is the first thing I do when I download them all is I start pinging you if I didn't get something where you're identified. Because if your lab report is late, I want you to a chance to turn it in late rather than not at all. Give me your abstract, meaning a paragraph. Here's what we were trying to do. Introduce the problem. What did you do? What were your results? Like in this particular case, I expect to see what your source files look like, what your test bench looked like, what your test vectors looked like, and what your results in Model Sim look like that photograph that I just shared. What did you discover? What did you learn? Who helped you, or who did you help? And if you think that I need to change the procedure in any way, which might help future students, that's what I am expecting from you. Make sense?
Yes.
Any questions about that from anyone?
Yes. If we do collaborate with another group to help them out or to receive help, what section of the lab report would you like that to be included on?
Oh, in the tail end is fine. If you help somebody with their tools, which I encourage, say we helped these people, and I will look for a comparable message in their lab report saying we got help from this guy or this lady.
I see.
Right? And I don't want you, I can't prevent you from sharing your answers, but if you use different names for every variable, it's easier to convince me that you didn't copy it from anybody. Because the first thing I do when I grade everything is account for everybody's report. Make sure that I've identified that I have a report from somebody or some team. The second thing I do is I look through them all to see if anybody looks like they just copied somebody else's stuff verbatim. Those people will get careful further scrutiny. If they keep doing that, I'll report that to the professor, and there are strict procedures at the university to use in case that we catch people cheating. In nearly 4 years of teaching at this school, I haven't actually caught somebody cheating yet. I've had some suspicions, but I haven't had any proof. And I hope that I don't find any proof this time. And again, one way you can prove to me that you're not cheating is rename everything. Because that means, oh, that's not his code or her code. Right? And otherwise, again, I do encourage you, if one of you runs into a problem, I can't get this to work, connect with each other, share screens, and they can say, oh, you didn't connect that right, or you made this typographic error. That thing is named that, and this is named that, and those names don't match, and that's why it doesn't work. Okay, you fix that. That's good. I'm happy if you help each other learn. And it's 1 o'clock. So if you'll forgive me, I would like to close this meeting and wish you all luck getting through next week, because you don't have to finish by next Monday. You have to finish by a week from Monday. And I'm going to close this meeting and go help my capstone students.
Thank you for everything.
Sounds
All
good,
right.
Joe. Thank you.
All right, I'm going to stop sharing and hang up. Leave this meeting.